Hey everyone, my name is Jakub and I'm a machine learning researcher in Avast. This is Mikuláš, who's also a machine learning researcher in Avast but in AI team. I'm from big data team. You may know us, especially the Polish part of... can you? Well, most people may know us from this.
Baza wirusów programu Avast została zaktualizowana.
So we are a security company and we have around 400 million customers, which means that we have a lot of data and bad guys never sleep. So there's a lot of data about botnets, malware, plenty of such things. So malware analysts cannot by hand sift through all these things. So we're trying to put as much of machine learning in our work as we can.
So we'll just today briefly talk about what deep learning is. We'll just review it because I guess you already must know well by now, if you haven't before. And then we'll just look at what the distribution means in this context, why we could need it or why we don't need it, maybe sometimes. And then we will just mention a couple of frameworks and some approaches that are commonly used to do distribution in deep learning. So by deep learning we will... thanks. So by deep learning, we will usually mean just having some neural networks, usually large neural networks, because if they are small, it doesn't make sense to do some distributed deep learning. And then we will talk about optimizing them fast and scaling them to process a lot of data in a short amount of time, or in a reasonable amount of time, let's say less than 1 day or something like that, hopefully. Well, the need for distribution, it arises from the fact that deep neural networks are fortunately or unfortunately known for scaling really well. So if you had then an infinite amount of resources because some companies have like also kind of infinite amounts of data, like images from streets or I don't know, some audio recordings from your Android phones secretly, then you could probably, with infinite resources, be able to process almost infinite amount of data. This is an example of some vision tasks where you can see that even when the order of images goes to millions, the neural networks just keep scaling up. And so assuming you can process millions or even billions of images, you will still keep probably getting better results. So that's the motivation behind distributed deep learning.
And actually, like, if you have complicated enough model without even tuning all the parameters, if you just put more data, it just will work better.
Yeah, usually, fortunately or not, I don't know. Like the latest trends are obviously like getting into GPUs and TPUs in case of Google, and of course, and besides that, I mean, one machine can only carry so many GPUs, right? So whenever you have like 4 GPUs and then you need to do more, you just have to do distributed. You just have to go distributed, and like there are a lot of papers and a lot of research, and actually now probably the vast majority of research and papers uses distributed systems for the computations because it just requires and uses and processes so much data. Let's just talk briefly about 2 different paradigms of parallelism. The first idea you would probably have is data parallelism, in which you simply have, let's say, 4 copies of one model, and you have 4 machines, and on each of the machines there you have the 1 copy of the model, and you divide your training data to 4 subsets of equal size or approximately equal size, and then each model on each machine is the same model. It has the same weights, and then you just feed different data to each model at the same time, and you somehow need to consolidate the weight updates, the gradient, as to actually do the normal stochastic gradient descent, but like in parallel on, let's say, 4 machines. So there's 2 main approaches of doing it. The first one is the asynchronous approach. This involves having a parameter server, or let's say a parameter process, which runs on one of the machine or on a different machine, and this actually stores the weights of the neural network of the model. And each of the workers or agents before each batch receives the latest weight updates from the central parameter server. Sorry, the latest weights, the latest numbers basically, computes the new mini batch and sends the gradients back to the server, who in turn incorporates the new update into the central knowledge, into the central network. And then again, whenever another worker asks for the latest weights, they just get it immediately. The advantage is that it's fast, because the workers don't wait for each other. They just ask anytime and receive new weights anytime. But the problem is that theoretically, this can lead to some problems, such as you receive some weights, you do the update, but in the meantime, the server already has received, for example, the same update from a different worker, which is just bad luck, and it might slow down your convergence rate or accuracy. But in practice, this turns out to work pretty well. So it's widely used. Anything to add? Okay. The alternative approach is to use synchronous training, which means after each mini batch, the workers synchronize together. They synchronize by averaging their computed gradients, and so the final gradient after each mini batch is the average of gradients from each worker. Now the problem here is that let's say the workers are in theory they should be on average computing probably in the same speed, but the fastest one will always have to wait for the slowest worker in this case. And so this approach is kind of more reasonable, more safe, but unfortunately it's slower because the workers have to wait, and if you have, for example, a slow network, this can lead to this actually being the bottleneck and not the training itself. Another approach, completely different approach, is model parallelism. This is kind of a different story because here, so far we assumed that the model can fit into a single machine. If the model cannot fit into a single machine, then you need to distribute the model itself, the weights themselves, into multiple nodes, multiple machines. And this is how it can, for example, look like, right? We have 4 machines. You have 2 layers on one and different parts of the 2 layers on second and so on. Now the problem here is that this is not exactly parallel. This is distributed but not parallel. This is the difference between distribution and parallelism. Distribution does not mean that the computation runs in parallel. For example, here the computation first must go through the bottom 2. Let's say we are going bottom up. The computation must first complete on the bottom 2 machines, and only then they send the information to the top machines, and then we go back. It is the same story. So basically, this is needed if your model does not fit into a single machine, but it's slow and there is additional cost, of course, to communicating between the machines because the parts of the model have to share information in normal neural networks. In Avast, we use this for a couple of data sets or problems. This is just an example of what we can use it for. This is just a visualization of some executable file, doing some smart things to visualize the structure of the file, its headers and so on, some entropy stuff. But this is one of the big data sets we have, and we can run convolutional deep learning stuff in a distributed fashion on these images, for example. But we mostly, I mentioned model and data parallelism. We will, from now on, be talking only about data parallelism because we, so far, luckily did not need to use model parallelism because our models did fit into a single node so far.
Yeah, and we will be mostly talking about TensorFlow and its options because we just have more experience with JVM stuff, and this is just what we're using. And first way to run distributed training in TensorFlow, this is one of the APIs where you can easily done it in an asynchronous way. So you have to create, as you can see on the code, you have to create first TensorFlow cluster. Then on each of the machines you start instance of TensorFlow server. You have to put to the cluster the IPs and ports of your parameter servers and your worker hosts. So then you use, instead of normal TensorFlow session, you use monitored training session, which takes care of all the communication of the gradient updates, sending them to parameter server, this kind of stuff. However, as you can see, you have to either by hand put the addresses of your nodes, or you have to use some other software like Mesos, Yarn, or this kind of stuff. If you're lucky and you're following Google guidelines to use the highest TensorFlow API as your use case allows, you may be using the estimator API, and this is how the model usually can look in there. Basically, it's super simple. All the model description is in the model function, but you have to be lucky. To run this in a parallel way, there is a new distributed API for TensorFlow that you just add the first line, which is merge strategy, where TensorFlow automatically finds out the GPUs on your machine, and then it passes this to run config of the estimator API. And on single machine, you can run it on however GPUs, how many GPUs you have, just with one line of code, and then your model will be distributed to those GPUs in parallel. This will be synchronous training based on allReduce, where all the gradients are accumulated. Another option is Horovod, which is like a Python package from Uber that tries to take out the distribution code from your model code. You just initialize it. It works almost as the asynchronous TensorFlow that you also have to use monitor training session. However, the only change is that you have to use their own optimizer. And it's actually not that simple to just wrap your TensorFlow code for it, because you have to use, actually, you have to use it on MPI, for example, OpenMPI, which is basically a message passing interface that is like high performance computing option for sending messages between the servers and processes. And still, it's another thing you have to configure, so it requires even more knowledge for you to run it on multiple machines. This also implements synchronous training, usually also done with allReduce. Last option we would like to mention is the TensorFlow on Spark, which is basically another thing you can put on top of Spark and run your TensorFlow applications. Its main advantage is that you can run it on already existing nodes. If you have already Hadoop cluster with Spark, you just install a couple of libraries on them and you can run all your TensorFlow programs there, which is useful even just for scoring all your data set, because in many cases your data will not fit into a single machine or even a couple of machines on a specific cluster. It will still live on the Hadoop cluster. It has two working modes. Basically, first one, in Spark reads the data itself and passes it in memory to TensorFlow program. Another option, the TensorFlow program is started in the side of Spark executor and reads data from HDFS. And with the Spark TensorFlow connector, you can actually store your Spark data frames as a TensorFlow records, which will speed things up even more. How does it look? Actually, this is just the code you need for TensorFlow and Spark. It's pretty simple. However, all your model has to be inside of the map function where you import TensorFlow, you create your own model, and it's basically if you have an already distributed TensorFlow program, to run it on Spark, you just import TensorFlow on Spark and add 2 or 3 lines of code and it should work. In this case, Spark will take care of all the communication between the nodes, all the assignments of the devices, this kind of things. Just to quickly compare it, if you can just use the TensorFlow with the distributed strategy API, it will be just single node. But if you have 8 GPUs on one single node, it's still fine. And it's really the one line of code and it works. The Horovod for us seemed a bit slower because since it's this synchronous and it requires quite a lot from the network and we had our GPU servers in multiple places, it didn't work that well. TensorFlow on Spark was great because you can run it on existing Hadoop. So even if you just train your model separately, you can just store all your data in the Hadoop. And asynchronous TensorFlow scaled pretty nicely. It was fast. Just as many GPUs you add, the faster your data processing is, and it's actually kind of easy to write. So in the end, like why you may not really need the distributed version that you split your training into multiple machines and multiple devices is that the we are still not at the limits of the computation on single node for the GPUs. With tensor cores, with 16-point precision, it just still works on single machine. Plus, with the TPUs, you can run it in the cloud even faster. Still, the changes to make it distributed require some code, which is not always easy to properly write and configure. The main thing, though, is that you most probably will not need that complicated models. The simpler models are enough, and they're much more data efficient, so you don't need that much data, so you don't need to distribute it.
On the other hand, you can also, then the question arises what actually is distributed learning and what is not, or distributed deep learning. Because, for example, if you're trying to come up with a reasonable solution, what you may do, suppose you have like 4 GPU servers, it may be more efficient to just write a very simple script that will run a different optimizer on each of the 4 machines, or it will do the hyperparameter search on each of the 4 machines separately, right? So that's kind of distributed, but like not by the actual definition of distributed deep learning, where it means that you like one training process is across like multiple nodes. What you can often do, and what is probably even better for experimentation, is to simply run different models on different nodes. And it's like, because typically we still need to do some hyperparameter search, and if you have multiple nodes, it's probably a good idea to parallelize at least this stage of development. Although we did not consider this as distributed deep learning.
Thanks. That's all for us. We had to do it pretty fast because we have a plane to catch. If you have any questions, feel free to write us. Thank you.
Thank you.
Okay, let's move smoothly to the Ignite talks. I think the first person is Mario on the list. Do we have Mario Tremel here? Thanks, guys. Nope. Okay, so Krzysztof Rogoziński. He was here a minute ago. All right, let me check who's the third person. I just remembered 2. Dawid Rymarczyk. Okay. Do you have a laptop? You want to show something?
No,
okay.
The laptop. Because the idea is pretty simple. So, who plays the bridge? This card game. Who plays the bridge? Not much. Do we have any enthusiasm of a bridge? That it's watching the bridged videos on YouTube and transmissions, analyzing the cards and so on. Is there any one person that does such things? Yeah. Good for you. So. My colleague and I, during the studies, he's a bridge world master, developed, come up with a problem that on bridge tournament, there are people who are sitting next to the table, and they often don't know anything about the bridge. So they are sitting and watching the people who are playing and putting into the internet the cards that were played. And our idea was to create a solution that we can take this card game and have it flawless, or more flawless than it was before, because those persons sometimes, very often, makes mistakes. And people who are enthusiastic in bridge, they basically are upset about poor quality of the transcription of the bridge. And as you know, all know that bridge is very exciting, so we don't want to spoil the fun for those people. So our solution was to buy a Raspberry Pi, connect 2 simple web camera, and on the tournament between bridge players is a border. So on the border you can place the cameras and Raspberry Pi with single energy source, and then start to read the both half of the tables, because this is a game with partners, and they do not need to see each other because, well, I can blink an eye and say, oh, I've got 4 aces. So that will be cheating. And simply, we found an algorithm that is using the AlexNet that classifies the cards that are already on the table. And it's not quite simple, because we need to firstly be resistant to all conditions like different contrast, lights, and so on. So we just done the simply thresholding, but it was adaptive. Then send those thresholded images to the server, which with the sliding window cutting out the 60 by 60 pixels and resizing it to the 224 by 224 for AlexNet. And pushing it through the AlexNet, we get the precise classification of the cards that were played on the table. But in bridge is one specific person. This person, when the licitation comes over, is putting all cards on the table and showing it to the partner, because the partner is the player who plays also those cards. And there is another problem that needs to be solved in such a system, because all cards are visible. So we constantly need to monitor what cards were visible from the scratch, from the beginning of the game. And when the card is disappearing, it's thought that it was played. And then when 4 cards were played from 4 different people, we know that the one round was completed. And there is one assumption, that we know the cards of the players, because on bridge tournaments, each table is playing the same sets of cards. So previously they are defined, and we have access to those. And this is our simple solution, that for those little world of bridge enthusiasm, we can make the life easier.
Thank you. I think, do you have questions to David for that? Anything? Or you can catch him afterwards. All right, thank you so much. Another speaker. Hold on, we have to set it up. Just. And give me that.
Where do I hold this?
Hold on. Yeah, it works. You'd have to stick to 5 minutes. No just problem. Yeah. 4 minutes. You can go smoothly, slowly, so everyone can catch it. Okay. So Christopher Wozinski, another Ignite talker.
Hello. Today I'll be presenting pythonlinks.info. It has the best Python videos from the best Python conferences. Currently 822 Python videos. The problem it solves is if you go to YouTube and you search on Python, the second one is 4 years old. Python's changed a lot since then. The third one is on Monty Python. The first one it's really good training, but it's 4 hours and a half. So on my website, when you go there, I have a time index so you can find it. And the fourth one is also a very good talk on both our sites. If you go to pyvideo.org, they have over 14,000 videos, but they go back to 2008. Some are really out of date. They have over 2,000 tags. If you can find your tag, you can click into it. But they don't sort which is the best one. When you come to pythonlinks.info, on the home page, you can see the 10 best talks. They're ranked by upvotes versus total votes. You can see they all have perfect scores. They don't have any downvotes. That's why they're the best talks. If you click into a particular video, you can see the video, you can see the conference description. Often I have to pull the conference description in on the website. Sometimes I can find the links to the talks. Sometimes I have to delete junk that's in them. The rest of the website is organized as a tree of categories. For any branch of the website, you can see the best videos in that category. You can also see the list view. Here we have, oh, I have it right here. Here we have the subcategories: machine learning, data science, parallelism, Python, and people. This includes how to run open source project, organizations, management, job seekers. A whole section on Python skills, beginner, advanced, Python software, and it's all organized as a tree. So when you go to the desktop version, desktop.pythonlinks.info, you can see this whole graph of the tree. The root of the tree is in the middle. It's JavaScript. It's really fast. You can hover over it with your mouse and browse the tree. Here you see the best talk from last year's PyData Warsaw, and the indentation tells you where you are in the tree. It was on tensor traffic. We can click into the conference, and we can see the 10 best talks at last year's PyData Warsaw. Very soon I'll have the votes up for this year's talks on PyData Warsaw, but there's a difference between the votes and what people recommend. So if you send me your personal recommendations, I'll put that in, and the results will be a bit different. You can search. When you search on a Python conference, you see all the talks in that conference, but it's much more useful to search on something like data science software. And there's a category. There are no talks ever call themselves data science software, but there is such a category. And you can click into that category. And you can see here, this is not the best view, this is the list view, because if you're interested in software, you're interested in some particular library, and then you can go into that branch of the tree and see the best videos on that particular software package. So I do all of this on a graph stored in an object database written in Python. It's really easy for me to do calculations on trees. If I tried to do this on top of a relational database, for every node in the tree, I would have to do a join across multiple tables. If I tried to do this in pandas, well, pandas have a statically bound parent pointer, but I'm using an array of dynamically bound child pointers. So it's really good to use a object database written in Python, really easy. And I also do calculations on the tree, on the JSON tree in JavaScript on the client. I'm looking for people to help me with this now. It's quite mature. I do a pretty good job of sorting them, but I'm not an expert in any particular library. What I need to do is work with the open source libraries to make sure we have all the best videos in that particular category. That's starting to happen. So if you'd like to help with a particular library, I'd love to talk to you. You can go to the website. You can click on the menu, and you can receive updates. And when a new conference comes in, I'll send you, when a new conference is indexed, I'll let you know. I invite you to follow me on Twitter at PythonLinks. The menu option also has a contact information. If you go to Twitter, you can upvote. You can retweet some of the tweets. There's one of the, I think it's the fourth tweet, links to the pull request on GitHub for awesome Python. Thank you very much. I have some business cards and flyers I'll hand out too.